In this vodcast, what we're going to do is we're going to look at whether or not a pair of lines in 3-space are considered skew. So remember back to an earlier part in today's lesson when I showed you this image here from your course textbook. Okay? And this one specifically right here. Lines are skew when they are not parallel and they do not intersect. There is no solution. So with this example, we need to show two things, and that is the lines are not parallel and that they do not intersect in order to establish that the lines are what we call skew. So let's start by considering whether or not they are parallel. Okay, so the first part of our solution is going to be devoted to determining um, if the lines are parallel. Okay, so we're going to test for parallel lines. So let's have a look at our direction vectors. Okay, we'll name them specifically in just a moment. We have this one here, 1, 2, 3, and 2, minus 1, minus 1. So we're going to let or designate M1 or vector M1 to be 1, 2, comma 3. And we'll also let M2, vector M2, be 2, minus 1, minus 1. Okay. So what you can see is that in this case M1 does not equal any particular scalar multiple of M2. Okay. So because of that, what does that imply? It means that our lines are not parallel. So L1 is not parallel to L2. Okay. Now, that's not quite enough to show that the lines are skew. We do now have to focus on a second part of our solution, and I'm just going to call this POI. We need to look for a point of intersection. So let's run through the process of doing so. So recall that our first step, okay, step number 1 in terms of doing so was to write the parametric equations. So let's get these set up. Okay, so our first one is going to be, so let's go line 1. So we'll have 3 equations, x, y, z. So x will be equal to 5 plus s. Y will be equal to negative 4 plus 2s. And lastly, z will be equal to minus 2 plus 3s. Okay. Line 2 will now also have 3 parametric equations. The first one being x equals 2 plus 2t. The second being, you can see that the second y value, that is from line 2, is 0. So we simply have a t value. So minus t, and then our z will be 1 minus 1t, or 1 minus t. Now the second part of our process is to equate or set equal our x's, y's, whoops, and our z's. So let's do that. So let's start with the x's. So first equation, we'll have 5 plus s is equal to 2 plus 2t. Through the middle here, we'll list the y's. So minus 4 plus 2s is equal to minus t. And lastly, minus 2 plus 3s is equal to 1 minus t. So we'll group our s and t's to one side, constant term to the right-hand side. So we have s minus, let me write a cursive s because that kind of looks like a 5. So s minus 2t, and we'll have 2 minus 5 on the right-hand side, is negative 3. We'll do the same thing for the equation in the middle. So we'll bring the minus t over to the left-hand side. We'll have 2s plus t. Constant minus 4 will become plus 4 on the right-hand side. Last but not least, our final equation would be 3s plus t is equal to 3. So the right-hand side, that 3 comes from 1 minus minus 2. So let's number these equations off. We'll call this 1, this will be 2, and this one will be 3. Now at this point in time, our goal is to search and or find a point of intersection. So what we could do is to look for two equations where it might be easier to eliminate one of the variables. And we can see that that will happen here with equations 2 and 3, both of them bearing a positive t term. So with that being indicated, let's go ahead and solve. So we'll take these equations, 2s plus t and 3s plus t, and what we'll do is we will subtract. So we'll take 2, and from that we'll subtract 3. So we can see that the t terms will cancel. 2s minus 3s is going to give us negative s equals 1, which means that positive s is minus 1. So we have a solution for the parameter s. Next, as we noticed in class, we will substitute. Okay, so we're going to set s equals minus 1 into one of the equations. So have a look to see what might be most suitable of a choice. So either 2 or 3, it really doesn't matter. Let's go with 2. So we'll have 2 multiplied by an s value of negative 1 plus t equals 4. So in solving this, we'd have t equals 4 plus 2, right? Because we're going to subtract negative 2 from the left side. So we'd have positive 2 on the right-hand side. So t is equal to 6. Last but not least, what we'll do is we need to check to see if our s and t values are suitable parameters for equation 1. If they work with equation 1, that is right here, if they work here, then we know that there would be a point of intersection, and then we can move forward and solve. That would mean the lines are not skewed. So let's see what happens. So we're going to use a different color here. Let's go with purple. So let's set s equal minus 1 and t equals 6. In number 1. And equation number 1, let me have a quick look back on this. We have s minus 2t equals 3. So I'm just going to rewrite that. I'm going to double check, make sure it's right. S minus 2t is minus 3. Okay, so let's substitute the values in. Let's go with the left side, right side form. So we'd have s equals negative 1, as I believe that's what we had figured out for s, and t is equal to 6, so minus 2 by 6. At the end of the day, it's minus 13. The right-hand side equals minus 3. So what you can see is that left side does not equal right side. Okay, so since the left side is not equal to the right-hand side, what we can say is that there is no point of intersection. And I'm going to be brief by using POI. So there is no POI. So therefore, line 1 and line 2 or skew because of the fact that they are not parallel and they are also lines that do not intersect. Now, last but not least, um, depending on the application, it might be important to determine the distance between 2 points in 3 space, between 2 lines in 3 space, or as we might see in the future, between 2 planes. So we're going to determine the distance between the following pair of skew lines. Now there is a process for this, and it will probably all pan out or come out in the form of 2 steps. Okay, so what we're going to do is to apply a particular relationship. So in terms of our process, our first step is to apply a formula that determines the distance, okay, between skew lines. And what that is the following. We take the magnitude of the vector, we call it P1, P2, and I'll write a few notes on this in just a moment, but P1, P2 is formed by 2 points on the line, okay, or on the lines. P1 would be on one of the lines, P2 on the other, and these 2 points happen to be those that are closest to one another. Okay, and what we'll do is we'll divide that by the magnitude of n. Now, n in this case, let's just write a couple additional notes on the topic. So the vector n is what we call a common perpendicular. Now, the common perpendicular occurs between the points on our skew lines that are closest together. We end up finding, okay, another nugget of information here, we end up finding it as the cross product of the 2 direction vectors that we're given. So up here we have M1, okay, that would be this one here, and then M2 would be here, okay, that's our M2. Last but not least, when we're going to look for P1, P2, that is to calculate P1, P2, we need 2 points off the line, and those we have before us that are these here. So P1, P2 can be found as follows, and I'm just going to actually do this right now. The second point, P2, is 2, 0, 1. That is the vector or component representation of it, and from that we'll subtract 5 minus 4 minus 2. Okay, and we end up with, what do we have? Minus 3, positive 4, and positive 3. Okay, let's just double check that. Yep, looks good. So let's move forward in terms of calculating. We'll see if we can't keep the video under, we'll try for under 20 minutes. So let's go ahead and find the cross product of our 2 direction vectors. All right, so that's the next step in the process. Okay, in fact, I guess this would have been one of the steps. I'll just label this as a 3rd step here. And lastly, we'll see this as being the 4th step would be to apply that formula. So here we go with step number 2. So the normal vector would be cross product of 1, 2, 3, and 2 minus 1, 1. And as you go through the video, please take the liberty to pause as you need to in order to think about your work as opposed to just passively listening and copying, be an active participant in this. So in terms of cross product, I like to organize my work. So I'm just going to create 3 columns, IJK. Okay, I is the basis representation for the x components. Okay, so the first vector is 1, 2, 3. The next one is 2, minus 1, and 1. So I'm going to start by focusing on the x components. So I ignore the x's and I deal with the y's. So we're going to look at 2 by 1 minus the product of these two. So I would have 2 minus minus 3, which produces a 5. Okay, next I'm going to cross these out, and I'm then going to focus on, okay, let me redraw these. I'll just move that out of the way. Now we're going to focus on the difference between these products. So we're going to start with 1 by 1 minus 2 by 3. So 1 minus 6 minus 5. And last but not least, okay, and there's only one thing I did omit to do. That is, with the y components, we need to take the negative of that. And I know that a number of people like to do the operation a bit differently, so they don't have to worry about that double negative. Okay, so we take the opposite of that product. And lastly, let's cross out the z's components to calculate the z component, the cross product. And we have minus 1 minus 4, which is minus 5. So we've got the vector n, we've got p1, p2. We only need to do a couple more things. Okay, so here we go. Let's move on and figure out our final step here. Okay, so 3 has been done. That was here. 4 we'll finish off. So the distance is the magnitude of p1, p2. That is the dot product of p1, p2, and n divided by the magnitude of n. Okay, so moving forward, p1, p2 is, so we need the dot product of minus 3, 4, 3, and 5, 5, negative 5, divided by the magnitude of the vector n, which is 5, 5, negative 5. Okay, so let's deal with our dot product. So the dot product produces a scalar, and we'll take the absolute value of that as we're looking for distance. So we'll take the absolute value of, so we have minus 3 and 5, there's minus 15. We'll add on 4 5s or 20, and lastly we'll subtract 3 5s for 15. Now the magnitude of a vector in 3 space is going to be the root of the square of the x component plus the square of the y component plus the square of the z component. So numerator absolute value here, we have negative 15 and 2 of them. That's minus 30 plus 20 is the absolute value of minus 10. And we're going to have the root of, let's see, we have 325s, don't we? So we'll have the root of 75. So that would be equal to 10 over the root of 75. So as an exact value, that is the distance between those two lines, which are skew lines. Okay, so if we were to evaluate this, just to give it a little more context here, so let's divide here. Let's take 10, divide that by, let's open up some brackets here. We need the root of 75. There's the root of 75, close bracket, and about 1.15. Okay. So in 3 space, these two vectors are approximately 1.15 units apart, and that is the perpendicular distance. So what that means is that our skew lines, okay, if these are our lines in 3 space, then somewhere in 3 space we have the following. Okay, we'd have this distance here, which is the shortest distance between, sorry, that's 1.15, the shortest distance between our pair of lines that are skew.